We like regex with this, you know. Hey everybody, thanks for coming again after last reading group. This is sort of a follow-up, but not exactly. So for those of you who didn't come last week, we covered AI inference optimizations last week, like quantization and not transfer, what's it called? Knowledge distillation and pruning and so on. So for those of you who might, just a further explanation for the layman, AI inference is basically what you do after training. So you train a model, you teach it what it needs to know, and inference is when you extract that information. So you go in ChatGPT, you ask it a question. That is called inference when you take that information from it. So that is not exactly always the easiest thing to do. Sometimes it's extremely slow. You need to optimize it for specific hardware and so on. And this week we'll be following up by covering Groq, who have recently gone viral for their extremely fast AI inference. How is it so fast? Today we're going to cover that. And what is Groq? Groq is an AI. Oh, finally, let's go. Uh-huh. So Groq is an AI startup in the AI accelerator space. And what do they offer? They do not make their own LLM. Their main offerings are two things: an LPU inference engine or chip, and their own AI compiler, which is really blazingly fast. And why about Groq? So, like I said, they recently went viral for their insanely fast AI inference. So they inferred Mistral 7 billion at 500 tokens per second. So for comparison, to give you an idea of how fast this is 4 times faster than that offered by most of their competitors today. And you take the state-of-the-art GPU into consideration, like which is the NVIDIA H100. No matter how many H100 chips you put together, you will never reach the speed. It is impossible. Like no matter how much hardware you throw at it, this is the level of technical achievement Groq has achieved. Let's see, question. Mhm. Of course.
On the GPU, how does it actually, what's the problem? Like, just why can't you just like throw another GPU at it and make it go faster?
So if you throw more GPUs at it, you might be able to serve more instances and more users, but you cannot necessarily make it faster because compute does not scale that way. And you can to an extent actually. So if you have two H100s, you can serve maybe 64, a batch size of 64, which is 64 people at the same time at a really slow speed, like, I don't know, 100 tokens per second. So if you scale that up to 8, you can save the same batch size at 200 or so tokens per second. But beyond 8, you wouldn't have any significant increase in the token speed because you have reached the limit.
What exactly, sorry, I follow, like what exactly limit are you talking about? Just like quantization limits or?
No, so the reason it's slow at 2 is because 2 is not the idea. So 8 is not an optimization on 2, 8 is the default. 2 is lowering that so it works for people. So you cannot go above it, but you can go below it if you need to.
So is the idea kind of like if we were to assume just a single unitary operation of inference, we can do 2 plus 2 is 4. I can add a million computers, but if I need, or like a million chips, CPU chips, but if I need to compute 2 plus 2 is 4, it's not going to be any faster than just one chip.
So
at the limit.
Yeah, I like the example. So a better example would be, say you have 64 people who want to compute 2 plus 2, and you have 64 computers. So that is the fastest you can, even if you have 128 computers, you can only compute 64 times. But if you had 32 computers, you can still serve them, but it's going to be slower because you're going to do 2 on each computer, yeah? So you have a hard upper limit, but no hard lower limit. You can keep going lower and lower and lower up to 1. No, not 1, because the upper limit is defined by the number of instances. The lower limit is defined by memory. So at the bare minimum, you want to load the model with the weights, the activations, and everything. And that model is not going to fit on one chip because that model is about, I think I said last time, 220 gigabytes, and one H100 only has 80 gigabytes. So 160, you need 3 chips for the bare minimum.
Right.
Any more questions?
From the last slide,
Yeah.
you mentioned AI compiler, what is that?
So, and AI compilers, some you might have heard of include PyTorch. PyTorch is an AI compiler. So what it does is it takes your model, which it takes the graph you define, and it maps that graph to the hardware and actually does the computations necessary for you. Yep. It works exactly like a real compiler, but for AI.
LPU full form is?
LPU stands for Language Processing Unit. You're right.
Okay.
Yeah, they also call themselves TSP, LP or TSP. That is Tensor Streaming Processor. Yep. So they get up to 4 times the throughput, and this cannot be matched by NVIDIA hardware. But is the hype valid? Like I said, it is a massive technical achievement. But I also think the hype is overrated. It's not what everybody puts it up to be, which I will explain. But the reason for this is purely economical instead of technical. And I think that is also important for engineers to consider because everything you always do, you will have to take economics into consideration. Some things are just not viable, which is why it may be worth considering if it's worth pursuing. So speed. Why does speed matter? Isn't ChatGPT usable enough already? Why do you need to go faster? Oh, actually, maybe I should show you an example of using an example of Groq speed first. Let's go. I don't want to open ChatGPT. My history is on there. Kind of embarrassing. It's a little embarrassing. So let's go to Groq and test something out. Oops. Now, if you, huh? You're right. Oh no, they only have Mistral. Wait, where do I set it? Oh, interesting. I see. I didn't even know they had multiple offerings.
I don't think Claude is. Okay, that's the problem.
All is closed source, no?
Yeah. Yeah, it's not like OpenAI.
Oh,
Yeah, this is
yeah.
even faster. Does Mistral have a free Mistral has no free, so I'm gonna have to open OpenAI. Claude.ai. Okay. Is it CLAUDE?
Yeah.
You'll have to sign up.
Well, I'm just gonna open ChatGPT and fuck it.
What is a computer?
Hey, help me with this presentation I haven't yet prepared for.
Wait, so I can bring it up.
No, it's cool, it's cool. I got it. Yep, there we go. Nah, it's cool. You guys can see. Let's see what I've talked about. Deploying ML models, calculate run pace, get prospect. This is for Shell. Mac and cheese image. Well, I have no idea what that is. But yeah. Yeah, now let's look at an example of ChatGPT speed.
Do the same for it.
Yeah. You cannot see, can you?
Yeah. So you can hit enter, I trust you.
Now you can see the difference in speed. So I think if I had to put a finger on it, I would say this was about 120 tokens per second, 130, 120. And the other one was, they claim 500, but I think it's a little bit lesser than that. At least when we just checked it.
Question.
Mhm.
I'm guessing they're not accounting for like an network latency, right?
Yeah, exactly. So you never know. Yeah, it does seem less than 500, but that I didn't consider that. That might be it. And so you might say ChatGPT, even though it's a little bit slow, it's still pretty usable. Why do you need that speed? Is it worth putting all that extra money into? So with this super low latency, you open several avenues of AI use cases. The first one being chain of thought. So when you want to use techniques like chain of thought, latency is super important because otherwise the latency adds up in buffers and slows you down way more than you initially think, and it becomes borderline unusable. And the second is for autonomous agents. So LLMs might potentially have use cases beyond, like, in the everyday world in real time. And this involves making decisions at the speed humans do. Otherwise, people are not going to want to use it. A good example of an autonomous agent would be a self-driving car. Self-driving cars need to make a self-driving car needs to make a decision within a millisecond. Otherwise, it has real people's lives at stake. And the third is code gen. Code gen, again, especially when it's autonomous, really needs real-time generation. Otherwise, the bottleneck becomes the LLM responsible, and you never want that.
So for autonomous agents like self-driving cars, you probably have to process things like image data. So is it possible for this for not this specific chip, obviously, but like for them to create a chip that is able to perform a convolution or some a similar process like that, or will it be sort of stuck to doing things on visual transformers or something like that?
You're saying, are there chips for CNNs out there already? So yes, there are. So you have NVIDIA has made a chip called the P100, which is put in cars like Lucid and so on, Lucid, BMWs and so on, specifically for self-driving. And Tesla makes their own in-house chip called the AP4, which is also for self-driving. They do achieve real-time decision making when it comes to CNNs. Yep.
Yeah, I was thinking about chain of thought, because from my understanding, just provide like a few examples and just ask the people that, why is that actually slower? Is that because like your prompt is physically bigger, so it takes some more time to parse the tokens?
From my understanding, when they're referring to chain of thought here, they're talking about chaining multiple models and maybe say a Lang chain pipeline or something where the latencies from the different models add up, and the final output, which you actually want in your use case, is going to be extremely unusable because you have, added latencies. You cannot work real time with it. You have to wait for the entire thing to happen first.
There are also like very complicated approaches to chain of thought.
Well, like React.
Proper like tree searches using chain of thought.
Oh, I didn't know that. Can you tell
Yeah.
more? Can you say a little bit more about it?
Yeah, so the idea behind the chain of thought generally is we have a dialogue, or the bot has a dialogue with itself and tries to reason out the steps or the result in a step-by-step manner. And at times there are multiple options that are useful, right? So you basically evaluate two trees of
Oh, that's going to blow up.
yeah, and then you ask the LLM to self-evaluate, hey, which one sounds better, right? And the LLM picks the one that sounds better and then continues to search that way in order to get you like a final solution that makes some form of logical sense in the ideal case. So it performs way better than this regular prompting, but at the same time requires a lot of dialogue and a lot of generation for a single response.
So your latency is going to be the sum of the latencies of all nodes.
Sorry, Google the tree of thought prompting from prompt engineering side. I think that is something very good. Tree of thought prompting from prompt engineering side. That's what I did. I did my presentation from prompt engineering. Yeah, that one. And scroll down. There it is.
Makes sense. But the latencies for all these guys, even the ones that aren't selected, are gonna add up because you have to generate the text for that. Makes sense. And
We'll take some other examples on the side about other prompting techniques. No, like on the left. Like you got like
Ooh.
rapid actual chain of thought prompting.
I remember that from your presentation.
Huh?
I remember some of these from your presentation.
This is what I based.
Nice. I'm gonna save this.
Anyway, that makes a lot of sense.
Yeah. And Arif, you had to say something?
Yeah, it's a silly question about coding.
Mm-hmm.
For the like layman developer using like Copilot or something, what's the real like factor of improvement that we're gonna see there when compared to Groq coding? Just Copilot.
When it comes to that, I don't think there's anything that Groq itself adds, besides, I guess, more usability, even though I myself haven't had any problems with speed when it comes to Copilot. I think the code gen is referring to here is let me collect my thoughts. So it's the kind where the LLM compiles the code itself to see if it works and tests it and then gives you the output. I forgot the actual word for it. self-instancy. Yeah, things like that. For when it comes to use cases like that, latency is extremely important because it adds up again and again because like chain of thought, you have multiple prompts going on internally.
So can I consider it just like the addition or can it be basically a symbolic execution?
Yep, somewhat. Yep. So now we have established that it is fast and we want it to be fast. So what is the downside here? Like I said before, it comes to economics and it has been dubbed tokenomics by economists. So the first thing is that it is slightly cheaper than most popular chips out there because it's built using the 14 nanometer node process. So for those of you who might not know a lot about this refers to the transistor size.
Are you recording on iPad? I'm sorry.
Oh, yep. Now I am.
Were you recording Zoom?
The Zoom is recording, yeah.
Okay.
Yeah, but the iPad isn't. So this refers to the transistor size. When you design a chip, you design it and then you verify it and then you send it to a fab like TSMC to actually manufacture it. And TSMC has their own manufacturing processes. And who here knows what Moore's law is? Okay, perfect. So everybody knows Moore's law almost. So Moore's law basically is that every one, it used to be it's 1.5 now.
Now it's the biggest.
Yeah, every 1.5 years, the speed of chips is gonna double. So why exactly is gonna double? Because you have more transistors per surface area. So all your computations are done by these little guys called transistors. You have billions of these in your silicon. So since one transistor does maybe one computation for you, the more transistors you have, the more you can do. So if in a given surface area, you could fit 7 billion before, you could get a certain amount of computation out. But now that transistors are smaller, you can fit 14 billion in them. So your chip, even though it's the same size, is twice as fast. This is how you have laptops becoming faster, even with no major design changes. So transistor sizes in recent years have gone from 14 nanometer first came out in maybe 2015, 14. And if you look at it, nobody actually uses it anymore. You look at your phone, that's not 14 nanometer. You look at your laptop, not 14 nanometer. This is actually used for cheap appliances like car TVs and so on, because they don't need that much power. We went from 14 to I think 10 nanometer to 7. 7 came out just 3 years ago. And then now we are 4, just came out last year.
My phone is at 5.
Yeah.
5, yeah. So these are the major milestones, but you also have in-betweens which came out later. So 4 is the latest now, and H100 is 4, A100 is 7. These are all NVIDIA chips, the same. I use them as benchmarks because they're what everybody uses. And eventually you're gonna have 3 by next year, and 2 is already in designs. So NVIDIA H100 uses 4, while Groq's chip still uses 14.
You have a physical limit before, like you can start like having like electrons jumping into.
Yep. Yep. So the limit defined by physics, we don't know. So there has been no experimental confirmation, but it is expected to be around half a nanometer. After which we're gonna have to do quantum or some bullshit. Like there's nowhere to go after that.
Two is like a buzzword, right? Like I read about.
Yep.
Not
Yep.
exactly 2 nanometers.
That's a good point. Yeah. So when it says 14 nanometer or 4 nanometer, no, all of these actually,
Yeah.
none of these actually mean 4
Yeah.
nanometers. So this is there, a long time ago, like 20 years ago, it meant the actual size in nanometers, but people wanted it to sound a little more innovative than it actually was. So they kept bumping the numbers up, but the actual change in the size wasn't this dramatic. This is they call it the process node size. So you cannot tell they're lying. They can claim, oh, we never lied. We didn't say it was a transistor size. We said it was the process node size.
What's
Yeah.
what's the actual weightage of this? What's the actual transistor size then?
The actual transistor size of 4 nanometer is, I think, about 20. I could be wrong. Let me just look it up. I don't want to lie. I don't want to lie.
Then you sort of don't run out of market.
is
Oh, no, then they go back, then they jump with like the new 20.
Negative nanometer technology. Very negative.
So 5 nanometer, the gate pitch is 51 nanometers and the metal pitch is 30 nanometers.
Yep, there you go. It's not even 20, it's 50.
Yeah.
Yeah.
But gate pitch, I don't exactly know, but like, I think gate pitch is like the film side.
So the transistor, I'll have to pull up like the silicon diagram for transistor.
No, yeah, the cable, so.
Yeah.
3 nanometers.
It goes based on that.
Oh,
No, it's okay, I believe him.
That's the
So, because of this, like the reason I'm bringing this up is to show you that Groq is using a much older process node size and achieving better performance than NVIDIA at 4. So they have a lot of room to speed up here. So eventually, if they go from 14 to 4, they're going to be approximately 3 times as faster with no other changes, like no major design changes. You're only going to have to refab it. It has some internal like physical design changes because you have to move around things so that nanometers fit, but the actual chip is going to be the same. So, but what this means is that it is much cheaper. Since this is an old manufacturing process, each wafer for Groq costs about $6,000, while NVIDIA's H100 costs $16,000. And you might say that, oh, it's actually cheaper, but there's more to it. Question?
Of
course.
Actual chips.
How many chips in a wafer? So I think when it says,
Like, oh, it's like
Mhm.
it's very stupid, like, it's completely a lattice type spinning.
yep,
It's just like, those are wafers, like, how you on them,
Mhm.
right, like, you cut them out,
yep.
right, it's like, how many can you fit per wafer?
So it really depends on how many you want to do. So when I used to work at Tesla, we used to make chips. We used to get 25 chips on each wafer, but we did not cut them off because we wanted, so you know what an SoC is? A system on a chip, yeah? We called it SOW, which is system on a wafer. So we wanted 24 SoCs all connected by silicon and not wires. So it was like as fast as you can be. Our latency was 0 because it was all in the same silicon. So some people get the 25, they cut them into different SoCs. Some just keep them like us. Some get much bigger. So the rule of thumb is that the bigger you do, the lower your yield is, because silicon is really hard to manufacture. So a lot of your SoCs have defects in them, very minute defects, but they will result in non-deterministic computation because it's a physical defect. You can't do anything about it. Yeah. So you usually validate them before you put them out and you throw out the fake ones. So the bigger your silicon, the higher your surface area for defects is. So people usually stick to like a smaller size, but not small enough to make it expensive. So it's like 25 is, I think, the sweet spot. And so, like I said, Groq's wafer is much cheaper than NVIDIA's. And but they have some other things to consider. The first one is that the chip is designed by Marvel. So Groq does not have its own hardware engineers. They outsourced it to one of the big 3 chip designing companies. So when you have like uh people making their own appliances, for example, BMW, they have their own car computers. They have an no, they buy the chips from AMD, but let me think of a better example. Say you want to make your own chip, yeah? It takes a lot of effort because you need to hire maybe 50 hardware engineers, you need to have physical design engineers. It takes a whole team, it takes 3 years of design and so on. So most people who want to make their own chips don't actually make it. They make extremely detailed specifications and they outsource it to 3 big companies. One of them is Marvel, the other one is Broadcom, and the other one is I think it used to be Digital Systems. So go ahead.
When is TSMC fit in on this?
So TSMC is the fab. They manufacture the chips after you design the physics. They are literally just a factory.
Okay.
Yep.
So can we just go through the supply chain?
Oh, I might do that. Okay. How do I erase on this one?
Just hold on.
Oh, okay.
Like, yeah.
Perfect. So supply chain. Say you are the client. That's a really sad guy. And you want you want a chip. So there's two ways you can go from here. One, you hire a design team. I write so slow. But this is extremely expensive, so it's only done by big companies. Like for example, Google wanted to make in-house AI chips, but it's also Google that have a fucking $1 trillion. So they hired their own design team and they made the TPUs in-house. But say a smaller company like Oracle also wants to make their own chips. They are in the process of doing so, but they're not as rich as Google yet. They cannot do it by themselves. So what they do is,
Only $1 billion.
only a few billions, yeah. So what they do is they go and they outsource it to the big three design companies or other smaller design companies. And these guys actually do all the hardware design for them, the microarchitecture. But Oracle's going to give them detailed specifications. Like we want a general overview of this. We want to do this, this, this. We want these pin layouts so it fits in with the rest of our PCB, like our system and so on. And these both then converge here. And after the microarchitecture, which is like designing how you want your CPU pipeline to be, how you want your memory to be, blah, blah, blah. From there, you go and you do physical design, which is actually saying which transistors go where. It's a whole job description within hardware design. And then the PDs, and you validate this here until you're sure that your hardware is perfect, because you do not want any mistakes in your hardware. And then the PDs also validated over here until they're sure it works. And then they send it to the fab, which is TSMC, SIMC, Global Foundries, blah, blah, blah. And all they do is they take it and they manufacture your chips for you. There's a lot more nuance to it, but we're kind of going off topic here, and I'll probably, maybe another day.
Good.
So where was I again? Yeah, so their chip is designed by Marvell. So for every chip they manufacture, they have to give Marvell a cut because Marvell designed their chip for them. So they lose money over there all the time because they're not big enough, which is why hardware design startups are so rare. They're usually, it's very capital intensive, so they make others do it for them, so they lose cuts to them all the time. Besides that, they're fabbed by GF, which is Global Foundries in America. So this is both good and bad. Good because their supply chain is entirely in America. So if a war breaks out in China, NVIDIA is fucked, but they're not. They're safe because their supply chain is in America. But on the other hand, Global Foundries is not as big as TSMC. TSMC is so massive. Their volume is so just gigantic. They make it for very cheap for you. But Global Foundries is not that big. So it's relatively more expensive. So it says here a wafer for Groq is 6K, but if TSMC was making the same wafer, it's probably going to charge like 4K, 3K or something along the lines. So you have more cost over there. And then Groq has no external memory. Everything is on chip. Everything is on SRAM. It doesn't need to buy DRAM from external providers like Samsung or BK, Hynix or whatever. So it saves money over there because memory is very expensive too. So you have a lot of ups and downs here saying, so it's cheaper because smaller process node, expensive because Marvell designs it, expensive because Global Foundries, cheaper because no memory. Yep.
How much SRAM?
It only has 226 megabytes per chip, which is pretty low, but because it's 14 nanometers, they cannot fit a lot in it. Maybe if there were 4 nanometers, so SRAM memory is the most physically space-consuming part of your chip. So smaller process nodes usually means that your compute takes very minute amounts and everything else is SRAM. So if they were 4 nanometer, they would probably have like 800 MB of SRAM, which is a lot more. But also more expensive. Yep.
So does this not sound like actually everything is really good for them? Because despite all of these things, they seem to be doing really well, and then they have like a lot of margin to improve in the future. That's like low hanging fruit.
Yes and no. They have a lot of margin to improve, but because of these points, on average, their chip is more expensive than NVIDIA.
Okay.
So you don't want it to be expensive because people don't want to buy expensive things. They don't have the money for it. And yeah, and add on to this, Groq has poor batch size, extremely poor batch size. So to serve 64 users, I said NVIDIA H100 needs 8 chips. Guess how many Groq needs? 256 or 266? So that is a lot more chips they need, and each of which is more expensive than an NVIDIA chip. So it is not economically feasible for most third parties to buy it, which is what Bhavesh remarked the other day when he said that it is not scalable. How companies are not going to buy it because one, it's too expensive, two, it's too hyper specific. So this has extremely reduced use cases, which is kind of sad.
So, just to clarify, if I'm like talking purely in RAM, right? Each wafer that Groq produces costs $6,000. That's 220 megabytes of SRAM.
I don't know how many chips each wafer has.
Okay,
It's 220 times that.
how much do you think it is?
Probably let's say both are 25, but NVIDIA and Groq are 25.
Okay, so 25 times 226 megabytes, which is 5.
Honestly, 6,000 seems cheap, so I don't know.
Right?
Yeah, so probably way less than 25. 25 for 6,000 is a steal.
So, okay, I'll just compute half, so that's 2.7 gigabytes of RAM per wafer.
I actually have a breakdown on the next slide
Okay.
for you. You don't have to do it. Yeah. So this is from a guy named, so the citation is down there. You cannot see, unfortunately. Well, it's from a guy named Semi Analysis. He has a really cool newsletter where he breaks down the economics of the entire semiconductor industry for you. Does really good breakdowns. So this is him breaking down the Groq LPU system versus NVIDIA H100 in two layouts. The first one is optimized for speed, like I said, many systems. The second one is optimized for throughput, which is increasing the batch size and reducing the speed so you can serve many people at once and be cheap. So if you can see, Groq needs five, I don't know what model this is for, but this is a benchmark he's using. It's probably I think this is probably Mistral 70 billion or something, because 576 is a lot. So you need 576 Groq chips, and you only need 8 H100 chips. And each chip price is 1,000 and 3,700. So Groq comes out cheaper, actually, surprisingly. And then if you look at the complete cost at the bottom, I'm gonna have to minimize this. Yep. The Groq system costs you 600K, while NVIDIA costs you 30K. It is 20 times more expensive to run the same model. And what you get out of this is speed. So Groq came up with their own benchmark, economic benchmark called tokens per dollar. No, dollar per tokens. Tokens,
It was
dollars per token.
are you talking
or
about
something.
the 2D graph where they have the throughput against the dollars? Or like-
Yeah, exactly. It is that, yeah. So when you look at it that way, they are cheaper by $10, but when you look at it like in a way everybody else looks at it, they're way more expensive. So which is why it doesn't make financial sense to actually get them. So that is the biggest downside for Groq, in my opinion. And I only wanted to put this out there to kill their hype. Yeah.
This seems like a design a lot of stuff in the US, which is good, it's great.
Mhm.
In case of an emergency, but it also sounds like as soon as they export stuff overseas, they'll drastically cut costs, right?
No. So moving to TSMC will definitely cut some costs for them. But another one reason they need a lot of chips is because of their design, which uses no external memory and all SRAM. When you only have 220 megabytes of SRAM per chip, at the bare minimum, you need like 1,000 chips to fit 220 gigabytes, which is the biggest LLMs, just for memory. Like I said earlier, the lower constraint is memory, and the upper constraint is just a hard physical constraint for the number of users. So their lower constraint is extremely high because they don't have external memory. And they cannot have external memory because of their CPU architecture, which I will go into soon. So that is all for economics. And honestly, I wish I didn't spend this much time on this. That is not that interesting. And let's go into their tech, which is the cool part, which is their innovation here. So Groq achieves this using a super scalable system architecture, which is they can have up to 10,440 TSPs in one system. In comparison, Google can about fit the same because they are also super scalable, but NVIDIA only scales up to 256, which means after a system of 256 H100s, you cannot use more than that to serve a single model. no matter how big your model is. It's just unfortunate for you. So you're gonna have to need multiple systems. Question?
What is a TSP?
The TSP is one LPU, is one chip of theirs. They call it a tensor streaming processor. Mhm. So this follows the footstep of other commercial systems, some successes, some not. Like Google's TPU cluster, which is a massive success actually. It's the best superscale system out there in the world right now. And in my opinion, better than the H100. And then you have Habana's Gaudi. Habana is an AI accelerator startup, which was acquired by Intel last year. Gaudi is also a super scalable architecture, which works in a similar way. You also have Cerebrus, which is another startup doing a super scalable architecture. And you have Tesla's Dojo also doing the exact same thing. And we can go into why their architecture is so scalable. You'll see that Groq has taken it a step further than most other providers doing the same thing. So at scales that huge, how did Groq achieve such low latency? 10,000 TSPs is a lot. So one rack holds maybe, so one tray holds 8 Groq chips. So one server has 9, I think, trays. So that's 8,972. So for 10,000, you need about 1,000, no, 100, 150, need 150 servers. So you have latencies of 2 milliseconds for a server farm of 150 servers. Seems like an impossible task. So how did they do this? And the solution is to eliminate all dynamism and decision making in the hardware process. I will go over that on the white paper soon, so you can see what dynamism means in this use case. And everything in the Groq chip is software defined. The network is software defined, the scheduling is software defined, the counters are software designed, memory location is software designed. The hardware decides nothing by itself. So let's look into some simple examples to begin with. So first one, the network. I think all of you might have heard of software defined networks to some extent. So when you have let's look at a network topology, yeah? So you have a router and you have computers. So if one computer, so in traditional networks, the computers don't talk directly to each other, because what if you want to talk from this guy to this guy? Yeah? So you might have 1,000 computers here. You cannot connect them all. So you have a router or multiple routers in between them. So it calls address 1, 2, 3, 4. So say you want to send something from, okay, we'll actually show my new thing. Say you want to send something from computer 1 to computer 6. What is the shortest path? Don't care. The computer simply the computer simply sends the packet out to the router saying, I want it to go to computer 6, do whatever you want. So the router is gonna, the router is designed such that it's gonna look at the packet, it's gonna say, okay, 6. So it's gonna know where 6 is. It's all stored in the router in a lookup table. A lookup table, for those who don't know, is just a dict with the addresses for each computer in here. Each router has a copy of the lookup table. So the router is gonna say, okay, so 6. So I can send it either this way or I can send it this way. And it's gonna compute that this one is the shortest and it's gonna send it this way, yeah? But sometimes this path might be busy because 2 is also sending to 5 and 4 is also sending to 5 at the same time. So it's gonna say, okay, this is busy, so maybe I'll do this one to save some time since this is occupied at the moment. So these decisions are made by the router. So dynamic here means that it happens on the fly, which is you send the packet out and then the router on the fly decides, okay, this seems like the better option. I'm going to do this now. And it does this for you. And what Groq does is it eliminates all this. So this is a macro perspective between multiple computers. So now you want to look into something called NOC. It stands for network on chip. So when you have super dense chips with multiple cores in them, like your laptop has 8 cores, yeah? A supercomputer probably has more like 256 cores in it. So you want to convey data between these cores. Each core acts like a computer, and the router is defined in the actual hardware. It's not a physical location, but it's defined in the hardware, which makes these decisions on the fly for you. But since it's dynamic, the hardware spends several clock cycles making these decisions for you. And what Groq does is it eliminates all of this by pre-compiling everything. So before anything even happens, Groq says, okay, on clock cycle 512, 2 seconds from now, this is going to go to this way, and at that time, this is going to be busy, so you should do this. So everything is known ahead of time, thus saving you a lot of time. But how does it do everything ahead of time? We'll get to that soon. So,
I
Hmm?
didn't follow. So this,
Mhm.
saying that like, the clock or whatever the global state manager knows or has a prediction, like 500 nanoseconds in the future, router one is going to be busy.
Yeah.
Okay.
It knows, so since everything in Groq is deterministic, the compiler knows everything that's going to happen, is going to know where each tensor is going to be in the future, since it has a global view of everything in the system. So it can make decisions by itself, since it knows everything. In this case, the computer does not know what's going on outside itself. Yeah, the computer is a separate entity. So it gives it to the router, who collaborates with the other routers and then makes a decision. But in Groq's case, everything is global. One perspective sees everything from before it even happens, so it can decide how things. He's basically playing God.
So it's essentially a load balancer.
It is a really good load balancer, you're right. And it is load balanced ahead of time instead of on the fly.
How does that work? Like, why does it know? Like, if it's, I mean, purely deterministic makes sense, but isn't it dealing with external inputs as well? Isn't that cannot that mess things up?
So external input, sure, it exists. Yeah, it does exist. But when we talk about computations, we're talking about the actual computation graph here, which you get once you have a trained neural network. All these computations are talking about that graph and not the external outputs. No matter what external outputs you have, the weights are going to go the same way.
This is not purely from CPU perspective, but this is more after the weight model has been trained.
Yes, this is the model when it is in the CPU.
Okay.
Or the LPU, whatever you want to call it. So I want to give you guys a brief history before I explain more static versus dynamic. When computers were first a thing, they were extremely primitive, right? Everything was, whoa. It's not, it's not right. Oh, I'm stupid. I'm so stupid.
Yeah, you just write it.
Yeah. So when computers first started, like back in the 70s or something, everything was static. So what this means is that, let's see. Yeah, do you guys know what punch cards are, right? Back in the day. So you had to tell it how to do everything. It only did everything in a very primitive manner, and the humans controlled everything it did. So it was a lot of work for the humans, and you had to do different things for every different task you had, because the computer only did one basic function. So everything was static, everything was fixed, it did not decide anything. So from there, slowly, as engineers got better, computers got better, we moved to making things dynamic, which is the computer makes its own decision. A good example of this is branch predictors. So say you have an if-else statement in your program, yeah? You had an if-else statement in your program, X is inside F, X is a function inside if, Y is a function inside else. So say this is inside a while loop. A while true loop is going to happen infinitely all the time. So when this is panned out to assembly, it's going to be this thing multiplied by infinity. It's going to be this thing down again and again and again and again. It's not going to be in a loop. Not assembly, I mean machine code, like binary. It's going to be the same thing again and again and again. It's just going to do the same thing again. So another perspective to look at this is in the form of a pipeline, because everything enters the CPU as a pipeline of instructions. pipeline of bytes. Yeah. So this pipeline is gonna go and it's gonna have a branch here at the if. So it's gonna see if, and then it's gonna go from here, and then it's gonna go from here. And if yes, it's gonna do X. If no, it's gonna do Y, and then they're gonna merge back. Yeah. So this decision, 1 second, Jen, I'll get to you. This decision at if, it takes several clock cycles. So how it's gonna happen is, let me think, condition. Yeah, first, before X, actually, my bad. There's gonna be the condition evaluation here. So you're gonna check if the condition is probably like, I don't know, n less than 1,000. And if not, right? So you're gonna have to calculate n less than 1,000 every single time you go through, like in the infinite loop, every single time you check if n is less than 1,000, and you go again and again and again. So this takes a lot of CPU cycles to calculate that, to take m from memory, to check it against 1,000, and then make the decision. So to combat this, CPU designers came up with something called a branch predictor. What this does is it predicts your branch for you without actually checking this condition. So what it's gonna do is it's gonna say, you know what, I predict it's gonna take the first branch. So it's gonna go here and it's gonna complete this pipeline. And then somewhere along the line, I think it depends on the CPU implementation, but sometimes in parallel, sometimes while actually, doing the computation there, it's gonna figure out, oh, never mind, I was not supposed to do this. So it's gonna backtrack here and then go the right way. You might think, okay, that's extra work. Why would it do that? But the thing is, branch predictors can predict the correct branch at up to accuracies of 99%. So out of every 100 times, it only comes back one time. So it saves 99 times and it's much faster, right? All this happens on the fly. The CPU does this all implemented in the hardware, and the CPU decides. The CPU makes these decisions as it's going. And yep, question.
Curiously, what's the algorithm to do something like that?
I was just gonna say that actually. So you might, this baffles most people, but the most basic branch predictor is do what you did last time, which is if the last time you went this way, go that way again. And it has an accuracy of 65%, which is correct more than half the time, which is incredibly good. And if you go from just last time to a buffer of maybe the last 5 times, it has an accuracy of 90+%, which is insanely good just for having a buffer of 5 bits.
Wait, so then, the buffer of 5, does it mean that you're pre-routing the pipelines in each of the 5?
Exactly, the CPU is pre-routing on the fly.
So what is that? This example only has one if branch, right? But are you saying that, the buffer of 5 would essentially be 5 branches of this one condition?
No, this would be the last 5 times the condition was evaluated. So if all last 5 were true, the next time is going to be likely true too. Because if in this case, like n less than 1,000, n is going to go from 0 to 1,000, for example. So for the first 1,000, first 5 times is going to actually do it. And then the next 995 times, it's just going to look at the last 5, it's going to say true, to save a lot of time. And only the 1,000th time will have a different answer. So it's usually ends up being 90+% of the time correct.
So, hold on, last thing is just that, like, is there an agreement policy, like, oh, you have to get like 3 out of 5 for it to use this one, or 4 out of 5?
Depends on the implementation. It's up to you.
But in this example, the one that works 90%, what's the policy that they use?
I think it's all 5.
All 5?
Yep.
Otherwise, they just go with the alternative, or?
Otherwise they do the other one,
You
yes.
can actually like decorate your code for the compiler to include specific instructions. If you think this is likely.
Yep.
There's a likely pragma, so you can just tell the compiler to generate instructions.
And this is in C++, right?
Yeah.
Programs are-
You can hyper optimize your code that way.
That's cool.
Yep. And actually this is also considered primitive. Modern day branch predictors are pretty much a mini neural network in there. They can predict up to 99+% of the times correct. They are insanely complicated, convoluted, and they're insanely correct too. But this is also only in CISC architectures, which is like x86, because x86 is extremely bloated and extremely complicated, so it can afford to do that. But when you go to things like RISC, it probably sticks to something simpler like that. Question?
How complicated is like this addition? Like you just said, like, oh, just throw in like a neural network.
It's not an actual neural network. I said it's almost a neural network, which is exactly how complicated it is. So these words, I took them from Jim Keller verbatim. He mentioned in the talk that they're almost as complicated as a neural network. I really tried to get my hands to see the implementation on it, but Intel has kept it closed source, so unfortunately I couldn't. And he worked at Intel, so he knows, so I just took his word for it.
So if we go back to risk, right? Why is it a problem to branch commit on risk? I would assume the fact that they're fixed size and struggle will make it easier to optimize.
It might, but Risk's entire philosophy is to keep things simple. So they prefer not to be that complicated and let software, handle all that bullshit. You had a question earlier too, my bad.
Yeah, so you mentioned earlier that there is no external memory and stuff. Is
Mhm.
that because of this network architecture where you want complete
Yes.
determinism?
Yes.
So you don't, so any sort of randomness will be external and you won't have like a God's eye view of the whole thing. You
Mhm.
can't predict what will happen.
So the thing is, in a Groq system, no matter how many chips you have, it considers the pool of all their SRAMs as one memory instead of separate. So I can go into Tesla's Dojo architecture for here, for example. Okay, so we had
And great secret,
Don't worry about it.
I don't really care.
Okay, we all have the pinky prompt.
They don't pay me anymore. I'm kidding. Oh, this is being recorded. I'm kidding, by the way. This is public information. This is public information, by the way, okay? So we had 25 SOWs and each one had its own SRAM, okay? But they were not considered one memory. Each one maintained its own version of the memory, and they had a concurrency. What do you call that thing, bro? That one number you showed to say who has the mutex, yes. Yes, you have things like mutexes to ensure that the memory between each of them is actually the same thing. It's like that, they show the exact same thing. You have primitives, that was the word I was looking for. Yeah, no, mutex is right. Primitives like mutexes. You had primitives like mutexes to ensure that you had consistency amongst the memory. So if you want to know more about this, there's a really good book called, it's a textbook, no, on-chip networks. Yeah, I think it's this one. It's a textbook which goes over all of this, but it's also kind of extra. I wanted to go like over a page of it, but it's not worth it for now. But it's a really good textbook about this entire thing, and it explains about how the different ways to ensure memory consistency. So one is each SRAM has the exact same image, and they ensure there is consistency by by talking to each other. And the other one is each one has different memory. Each one operates independently, but is organized by a host CPU on the outside, things like that. You have multiple different strategies you can use. So what Groq does is it says no to all of these and says all of these addresses combined form only one memory. So if the first one goes from address 0 to 100, the next one is not again 0 to 100. It is 101 to 200. So it's all like it's one big pool of memory. So because of this, again, it has the God's view of the entire SRAM pool, and it cannot have DRAM. And DRAM is also dynamic by definition, is dynamic random access memory. Yep. So back to
There's really no virtual memory, it's like physical one-to-one mapping.
yeah, physical one-to-one for the entire thing, no virtual. It doesn't really have, yeah. Virtual memory by like definition needs DRAM because
Yeah.
that's this DRAM disk pulled in. So there is no chance of having virtual memory.
Yeah, direct one-to-one.
Direct one-to-one, which is also why you need so many chips. There's only so much you can host. Yeah, it's kind of sad, but it's really fast. So back to clock branch predictors. This is a mechanism most modern CPUs have. So what's the advantage of this? Like the computer does not know what code you're gonna write, right? You could write pretty much anything. Anyone can write anything. So it wants to optimize everybody's code, so it optimizes on the fly as it's going. If it didn't do branch predictors, it's going to be extremely slow because it's going to go the wrong way all the time. Yeah. But what Groq does is it says the compiler is going to know what's going to happen ahead of time. So we don't need this at all. Like we don't know branch predictor. We know what's going to happen. So we can just make the decision and not go the wrong path at all.
So what about cases like like mixture of exports? We saw mixed trial what is it? 8x7, right? For that, they have like sparse mixture of exports. So they pick top K exports for a particular inference. Now this depends on the previous weights and the softmax equations over those weights, over the weights, no, over the inputs, right? So it's not possible. How is it? How does Groq manage that when it can't predict? Like it can't predict what the top K would be, right? So how do they figure out which ones to select, and how do they deterministically set that up?
So that is a high level thing you're talking about. Those predictions happen at a much higher level. This, I just used an if statement to show you guys, but these things are extremely low level that happen at the machine code and CPU instructions level.
Okay.
At that level, sure, there might be some big decisions it might have to make wrong every now and then, but the smaller decisions that happen in loops all the time are always known ahead of time. Yeah, because after it enters the top K model, within the model, all the minute decisions, it gets all of them correct. But those big few and in between decisions, it doesn't really
So
matter.
branches exist in Groq as well.
They
It's
do.
just that we know like 90% of them
Yeah.
by default, and the remaining 10 that's fine. if it's-
Almost everything is known, so it's okay. Like that's sacrifice they chose to make, and it paid off. Yep. So things like these, like I said, they used to be static, so it was a lot of hard work, which is why we made them dynamic. But dynamic wasn't fast enough when we knew what we had to do, and we had to make it really fast. So we went all the way back to static. This is the same way all cars used to be manual gears. You move to automatic to make it easier. But when you want to race cars, you still want to have maximum control. So you go back to static, back to manual gears.
Right.
Exact same scenario.
So one question about like, so is the compiler prefetching the pipeline then? Like who's doing the actual job of making sure that the CPU always has like the pipeline ready to go? It's like
Compiler. The compiler does everything here.
Okay, and
Yep.
so does it also do the job of storing all this like buffer or whatever it's going to store?
Everything is software defined by the compiler. Yeah, it is a crazy amount of control they've given to the compiler. So this is a branch predictor is one example. Besides this, you have things like scheduling. Say your OS has multiple jobs. It's not going to have multiple jobs in this case, but say for example, it's going to have multiple things it wants to do at once. What an OS does is, actually I just learned this, but I forgot. I'm taking OS right now. But yeah, what an OS does is, it checks if your process is IO bound or CPU bound, and then based on that, it's going to say, okay, so say you have like 3 processes here and 2 here. It's going to say, okay, so your process is IO bound, huh? So you can go first. It sends this guy first, and then it sends this guy second, and says, okay, we send 2 of those. It sends this guy third, this guy fourth, this guy fifth. The CPU decides all of this in what's called process scheduling. It schedules the process. So Groq said no to all of this and said that we will statically schedule all the processes ahead of time. They said we know what all these 5 are going to be, so we can just define what it's going to be before it even happens. You can just say, like 1,000 clock cycles from now, these 5 are going to pull up. Just send them in this manner, playing God game.
So with this, since it all kind of happens in the compiler, is the compiler time significantly more than what it would be on something else?
Yes, good question. Yes, it is going to take longer, but these things are ahead of time compiled. So you only compile them once at the start, and after it's going to take longer then. But yeah, once you're compiled, you're compiled. No matter how many times you want to use the same thing again, it's going to be faster every time, so it makes up for it.
So does that mean that if there's like a new architecture for some model,
Mhm.
so this stop working?
Yep, you have to, which is why it's someone on Twitter mentioned that when you talk about the cost of Groq versus NVIDIA, you also have to talk about the cost of developer time, because devs have to write, target a whole new architecture, write the whole thing again from scratch. That's a lot more work you have to do now. And besides let's go over the slides. What else did I have there? We talked about scheduling. We talked about, well, branch predictors I don't have here, but counters. So the CPU has counters to ensure that all clocks are synchronized. Groq doesn't have that. It has software counters which manage all of this using an instruction. Then you have memory locations. So when you want to write to memory, you don't actually specify where you want to write. You just say, I want to write to memory. And then the computer goes and says, okay, this place is free. I will write there and store where I wrote it so you can pull it from there later. So Groq does not allow that. You have to manually specify where everything is going to be written ahead of time. Also makes it extremely fast, but also a lot of work. And then network. Well, network has been software defined for a long time. And I also explained it up here when I said you don't have the routers, everything is predetermined by the software. So the first big part of the Groq system is the network. It is also a major innovation in a way. So from their paper verbatim, they say to enable seamless scalability and preserve that programming model across multiple TSP elements, the network also needs to be deterministic. So within one TSP, we have confirmed that it is in fact deterministic because everything is known ahead of time. But what about when you have 250 TSPs in a system? What about between the TSPs? All of that needs to be deterministic too, which is why they have eliminated all routers between servers and everything is software defined. They only have cables. So let's go over some popular network architectures, yeah, at a server. Say you have a server farm with 64 servers. You have one big connection to the internet, so one fat cable. And then you have one switch or router. There's the same thing today, but yeah, you have a router. It talks to 4 routers. It talks to more routers, blah, blah, blah. And in the end, you have your 64 CPUs with servers. And so it scales like a tree, basically. This is called a fat tree topology. This is the most common topology used in data centers across the world, like AWS, Azure, Google Cloud, you name it. So if a computer in this server wants to talk to a computer in this server, what it's going to do is it's going to tell its router, hey, I want to talk to that guy. So it's going to see if it's directly connected. If not, it's going to send up there. If it's not, it's going to send up there, and then it's going to come here. So it's going to traverse the tree in what do you call that? I forgot my data structures. In order, yeah, it's going to traverse the tree in order from its from the original server to the destination server via the routers. So, but this is not when AI accelerators came into the picture, this is not exactly fast or low latency. You have too many hops. That is what is referred to low network diameter. So how is network diameter calculated? You take the shortest path between all the nodes and every other node. For example, between node 1 and 2, 3, 4, 4, 64, 2, and all the way to 64, and so on. And out of all these shortest paths, the longest shortest path is called the network diameter. And that is what you want to minimize when you're building a super low latency system like Groq or TPU or NVIDIA or whatever, H100 or so on. So this one has a super high network diameter because the longest shortest path would be from this guy to this guy. It's going to have to go traverse all these routers to the main router and then come all the way down here. That is an log n number of hops, which is way more than you want. Like, sure, it's not linear, but it's still a lot. So the solution to this is what Groq calls the dragonfly network topology, which is given you have 5, is basically everyone is connected to everybody. In simple words, everyone is connected to everybody. I think it's also called, no, that's not a mesh. A mesh is when you have, this is called a mesh. So if you have more, this guy is not connected with this guy, but it's still pretty fast. It's no log of n. This is a mesh, yeah. I called this a mesh by mistake, the one on the left.
No, this is, you could say this is a mesh, like why got
Really? Oh, I didn't know that. but they call this a dragonfly topology.
It's like one with like every single node, like 255 connections.
Only connect-
Yep.
Oh,
So I will go more into it in a bit when I open the, honestly, I don't think I have time today. Maybe one day if I do, I'll go over it.
We've already- so that- the way-
Yeah, but 20 minutes over, yeah.
Holy shit.
I don't, yeah, how many people are voting after this?
I prefer this original.
I'll go over the topologies real quick, finish within 5 minutes maybe. So they call this a dragonfly, and Google TPU has a really cool topology too. You might want to look into if you're interested in that. So say you have, again, same like before, 9. It's like this, but with a twist. The edges connect to each other, so the network diameter is reduced dramatically. So the end-to-end is not through the whole thing, but rather through the overhead cable. So the diameter goes down by a lot. And this is not the only twist actually. I cannot draw this out, but take this over here and make it an actual cube and connect the ends of that too. So the whole thing is in a cube and it scales cubically.
And
And
it's 3-dimensional.
yes, there's a 3-dimensional architecture and it scales cubically. So it can scale to a lot of nodes very easily. And keep the diameter small at the same time. They call this a toroidal network topology. They came up with this themselves, like is there no architecture. They have this paper called, they have this paper called Apollo. It's about the entire data center networking architecture. Really cool paper, very easy to read. I highly recommend reading it. And they also actually, Google not invented, but came up with their own network switches, which are optical instead of electrical. So you know how electrical switches have a hard limit. They can only do, for example, at this moment, not even a TB per second. They're like 128 gigabytes per second. So Google said that why have wires at all? And they made it optical switches with mirrors and light traveling between them. The information is traveled as blips of light. So it travels at the speed of light. Your theoretical limit is the speed of light, which is how many ever, which is fuck you gigabits per second. Yeah. Combine that, this is why Google is almost as impressive as Groq. So honestly, they might come out with something as good as that in the near future. You might want to keep your eye out. And it's one of the reasons why their API for Gemini is so cheap compared to OpenAI and Mistral and Llama and everybody else, because they have a really good, it's cheap for them to host it. They have a good system architecture. So back to Groq, they use Dragonfly to ensure that they remain fast too. And direct network is again solved by Dragonfly, which means that you don't have to go through a router and everybody just directly talks to who they want to talk to. That is their two main goals when it comes to building a low latency network. And because of this achievement, they have complete determinism over their entire system, because you don't have a router, which means you know how everything's going to be. There's no on-the-fly decisions. Now, that was my last slide, so we're moving on to the paper now. To go to their network. Question.
So, the network configuration is determined by the compiler, right? The compiler figures out.
Yep, but it is sort of hard coded in a way.
So if
As
they
in
want
like,
to like expand, they'll have to recompile everything.
huh?
So if they ever want to expand to like, let's say they want to add another element, they'll have to recompile everything.
Yep, in a way, yes. So it's a lot of work in that way, but I think they have software which does it for them. They have some generation. So down to their topology, yeah. So within their compiler, they have something called a virtual router, which has 32 slots, which is why when it comes to a system of 32 TSPs, they are insanely fast because they all are controlled by one virtual router. So their levels of speed go from 32, no, first within the system, which is one tray. So everything has like in-tray wires, you have no routing at all, blazing speed, almost silicon speed, and then you scale up to 32, which use one virtual router. And then they scale further to 200, see where that is.
264.
264, yes, the scale 264, which is second fastest, third fastest for them. The reason they can scale 264 is because when their output pins are taken into consideration, they have they have 7 pins, one for each within the tray, and 4 global pins, which is they can connect anywhere not specified at the moment, like the actual hardware. So you can connect those 4 pins to 4 other trays, and you have a combination of 264 TPUs now, which is, I think, the reason they actually went with Mistral 7 billion to show off their speed, because Mistral 7 billion can be fit within 264 nodes, and they get that extra boost of speed so they can show off. So if you were to go from a 7 billion parameter model to just 9 billion, you would not get nearly the same speed, even though it's just a little bit more. It's kind of shady, but I would do the same. Yeah, you gotta show off when you gotta show off. Can you guys read the paper properly? Let me make both screens laptop for now.
Can you drop a link to the paper?
Oh yeah, for sure I will.
Like,
I can
okay, stop it. There's no-
Going over their paper, where was I again? Let's just go with the system heading, I mean the titles. Introduction, blah, blah, blah. Scale out system organization is where they explain how they plan to scale out. So the first part of that is their topology objectives, which I talked about, low network diameter and direct network. And they solve this by using the Dragonfly network. And the second is a system packaging hierarchy, where they explain how the TSPs are laid physically, which, like I said, you have one tray. And so if for those of you who don't know, servers look like this. You have one big CPU looking guy with 9 trays inside it, I think. These are all like industry standards. No matter where you go, it's going to be the same thing. And each tray for these guys has 8 chips. This is their physical hierarchy. It's not that important. And chip-to-chip links and flow control. So chip-to-chip links is wires they have within their tray to talk to within a minute system. These are blazing fast at speeds they claim are way more than 30 gigabytes. Oh, it's 30 gigabytes per lane, and they have 8 lanes, so it goes at 240 gigabytes per second. So for this, they use something called I forgot what the cables are called. They're extremely fast. SerDes. They use something called SerDes lanes. This is also an industry standard. They use the same thing at Tesla. What SerDes stands for is serializer, deserializer. All it does is it serializes your data, sends it over the cable, and deserializes within the cable itself. So it's extremely fast.
What is AWG? That's just so it operates over 30 gigabits per second over
That's wide gauge, I think,
Wait, I didn't know that.
American wide gauge.
Oh,
I forget what, I don't know if it's called European wire, I forget the other one,
I see.
but that's, yeah, I think the higher the, like the number, yeah, it's the higher it is, the smaller it is, and then the lower. it gets bigger. Yeah.
Mm-hmm.
American Rally.
Mm-hmm. So they also say they keep the cable short to reduce latency. All this is not important. Everybody does this, so it's nothing special. This is an important point where they say that the hardware is disallowed from asserting back pressure on the network, which is not disallowed, it never has to. So back pressure is, say, for example, when um, a network asks the hardware to provide it the result of a computation, and the hardware says, I don't have it yet, I was doing something else. It is what I do when I have to do things too. But yeah, that is called back pressure from the hardware. But in this case, hardware never has to assert back pressure, because the network will know that the hardware doesn't have it and just not ask for it, because everything is predetermined. And you know how like I said, the router has lookup tables. In this case, since the SRAM for each chip is part of the shared global memory, it uses the SRAM on each chip as a mini buffer to store where the packet should be sent, which is kind of scuffed but smart. And maintaining determinism in question.
Wait, so you said that that's all predetermined on the
Yeah.
ballot.
Mhm.
So why is there an answer not some sort of flash or something that's much cheaper?
It does not have flash. It only has SRAM.
Why, so if it's not gonna be, if it's not gonna be modified since it's deterministic, so why store it in RAM?
It's not going to be modified for a given model. You can host multiple models on it at different times. Each is going to have a configuration. Yeah, so it's not like it's going to be the same thing for the history of the hardware. It's for the history of the computation you're doing, like the history of the program you're running, right?
You can still like store that in read-only memory.
There is no memory. There's no read-only memory at all.
Yeah, I just was asking, I mean, I feel like that would be a good idea. I mean,
But the thing is, this, you cannot do it in read-only memory because you have to change it. You have to change it.
would you change it when you compile and upload the program?
Yeah, for different, like, for example, you have Mistral in it now. Mistral has a given configuration and it's going to be the same for as long as you run Mistral. But the second you want to load a Llama model on it, it's going to have its own config, and the compiler determines the config for it. So it is fast for, runs, but it's not so fast that you can just store it in the ROM and
Okay, oh, so you need to change like often?
you need to change, no, not often, but like for each use case, yes.
Okay.
Mhm. So they say that the collection of functional units on each TSP act as a single logical core. This is how all GPUs work, so it's nothing special again. So you have a multi-core, you have multiple cores on a single chip, which say you have 256 or so on. They all act as one logical unit, and their only purpose is to parallelize. They don't do different things by themselves. And it is scheduled statically at compile time, so you don't have to worry about saying which one has to do what. Yeah, this is where they talk about sharing the global SRAM without requiring a mutex to guarantee atomic access, because the same guy, it acts as a global SRAM. There's no concurrency here.
So this may be a dumb question, but given that there's just like 25 chips on the board, is that correct?
Sometimes yes.
Okay, well, whatever the design is, like there's 25
Mhm.
chips that actually store that SRAM. Is there any sort of software abstraction from the compiler that assigns like the 0 to 100, 100 to 200? So my point is, the one thing that confuses me, that like, who determines that definition of the memory addresses?
Memory addresses are baked into the hardware. Like the software doesn't do it. It is baked into the hardware straight up.
But what if, say, for instance, I want to add a new node of these TSP?
So memory addresses are baked into the hardware for a single unit. When it goes outside the unit, that is determined by the OS usually.
It goes below us here. So
Compiler does it, everything.
Okay, so compiler is the one where you're giving this basically page table abstraction.
Mhm.
So the compiler, sorry, the compiler is in the sense we have to compile it not only for every single model, but also for every single setup. So before we start running Mistral on my computer, I have to compile it for my computer specifically. Like assume my computer has the accelerators we need, right?
But it will never, because these aren't meant for personal use. Yeah, okay.
Assume I have something that just magically
Okay.
sticks it.
Mhm.
I have to recompile it for mine,
Mhm.
and if I need to put it on someone, run Mistral again on someone else's computer who also has the same accelerator, they will also have to recompile it if their setup is not exactly the same as mine.
Yep.
Wouldn't you need the specific chips
So that's
to
being like, if I
Yeah.
really want to run a
do actually run it?
Mhm.
that recompile.
So, okay, and then, so, but each chip, going kind of back to this question, each chip would still be 0 to 100 though, and then the compiler would figure out, okay,
Yeah.
the second chip is
Mhm.
actually 101, so.
Yeah.
Okay.
Mhm. So back to here.
Wait, is this what they wrote all of this in Haskell?
Yes. A good part of the compiler is written in Haskell actually, because one of their head engineers is a big contributor to the Haskell community.
functional program by the number of times they use the deterministic.
Yeah, also like program correctness and so on. Like they care a lot about this, which is why I said Mikhail would have loved this.
That's what they
Too
would
bad
do.
he had to go there. Huh?
That's what they would make money.
Yeah, they're not gonna be it. They're not.
It's the prophecy. They're all going to go.
They're immune to it. Yeah, see, program. So we can reason about program correctness. No, nobody cares about that. I'm kidding.
Mikhail does.
Huh?
I know Mikhail does.
Yeah. So this ISA is called the VLIW ISA. So for those of you who don't know about ISAs, an ISA is instruction set architecture. So what it stands for is you have a program in C or Python or Java, you compile that down to maybe assembly, maybe bytecode, whatever, which compiles down to machine code. And CPU does not just read the machine code. It needs a certain structure to the machine code. Actually, this happens after assembly. After assembly, how many of you have written assembly? Or have any experience with assembly at all? Like looked at it ever? Yeah, if you've taken 250, it counts. If you've ever looked at a .s file in your life, it counts. So you look at the assembly and you see that all their operators are extremely primitive. So you only have things like add, you have mul, and then you have move, good one. Sub, smart, yes, block, comp, yeah. You have things like this. These are all primitives. It's not going to have advanced functions like mean or min or max or so on, because all those can be reduced to these basic instructions. So these are called instructions, and the set of all these instructions is called the instruction set architecture, or the ISA of the CPU. There's three major types of ISAs. There's CISC, and there's actually just two. The others are not major. You have RISC and you have CISC. So CISC stands for complex instruction set computer. Yes, RISC stands for reduced instruction set computer. Complex, this was made or at least popularized by Intel with their x86 lineup of computers. So the reason it's complex is because it when it comes to 6 CPUs, the CPU does a lot of it for you. So it's great for general purpose CPUs like your laptop, which you have, and so on. So since it does most of it for you, the actual OS or the compiler doesn't have much to do. So it's great. Everybody loves them because of that, or at least loved them. But the thing with them was they were getting too bloated. They had way too many instructions. There was only, you could only get so much faster. You couldn't go faster than that. And you didn't need like 90%. This is not an exaggeration. 90% of the instructions you will never use in your life when you use a computer. It is that bloated, which is why RISC started getting popularity with ARM. This is heavily used in mobile phones now and server-grade CPUs. And ARM makes reduced instruction set computers, which are simpler, but the compiler has to do slightly more work. The OS, not compiler actually, the OS always has to do slightly more work, but it's okay because Linux has support for it. And now Apple making support for it is starting to make it mainstream within computers. And when it comes to phones, they're usually not complex enough to require a lot, so it's okay. And besides ARM, we have another one called RISC-V made by Berkeley. This is an open set instruction set architecture, which is anybody can use. So CISC is made by Intel, so you have to, either you can only buy Intel chips, or you have to pay Intel a hefty sum to use it. And ARM is made by ARM, and you have to license it from them. So for each computer you make, you pay ARM a small fee. And RISC-V is made by Berkeley and it's completely open source. Anybody who wants can use it, and all major tech evangelists are big fans of it. You can look at this like it's the Linux of instruction sets. Yes, completely open source, very small. It only has, I think, 64 or something base instructions, which is compared to CISC, which has like 2000 something. Yeah, that is the scale of difference we're looking at here.
Are there any like actual production computers that use RISC-V?
So many, yes.
Yeah,
What's like an actual like competitive one that we use compared to like a?
So it is not going to be general purpose. Most people who use RISC-V today use it for server grade or actually, when you look at accelerators, TPU is RISC-V, Dojo is RISC-V, and I don't think NVIDIA is RISC-V. NVIDIA is ARM, and you look at Gaudi, Habana, that's RISC-V. All major accelerators are RISC-V.
They do that because it's easier to optimize for, or because it's cheap and it's free.
Both, so it's perfect, which is why you might think, why don't everybody do it? It's because of one, familiarity, and two, existing infrastructure support. So the only problem with RISC-V is you have to start supporting it. And actually, Qualcomm is coming out with the RISC-V CPU for mobile phones late next year. So if it becomes a thing, hopefully things get better and everybody uses RISC-V. Ideally, in an ideal world, everybody uses RISC-V.
Just like everyone would use Linux.
Yeah. And just like the layman doesn't want to use Linux because they think it's hard to use, it's the same with RISC-V, where the average CPU designer doesn't want to use it because it's gonna make too much work for the guys making the OSs. Like I think as of right now, it is damn near impossible to have Windows on RISC-V CPU. You just cannot. It's Windows.
Sorry, Dad.
And after this, you have something I actually didn't know of until this itself. VLIW. It stands for very long instruction word. So what it does is it takes it a step beyond even RISC, makes even lesser instructions. The computer does even lesser and says, "Hey compiler, you're going to do everything for me. I'm going to be a bum now." So it only has very few instructions, but some of them are hyper specific for these kinds of use cases like Groq has. So you have instructions like send or receive, which help with guaranteeing the cohesiveness of the global memory of the SRAM. This is like move in Cisco RISC, but a little more elaborate. I don't know much about this myself. I'm gonna go home and read up more about it down the line. Hopefully, let you guys know if I do. And this is just talking about how the compiler makes a dependency graph, so everything is predetermined. Again, nothing special. I think every ahead of time compiler does that. It's a very popular PL thing. And a multi-TSP system. Yep. And after this, I am not going to present today. Yeah.
Okay, quick 5 minutes and then I'll be.
That was 20 minutes ago. Yeah. Hardware line counters. These counters are basically replacements for hardware clocks in everyday gen purpose CPUs. You have hardware defined counters, you have software defined counters, and you had one more thing I forgot. A runtime resynchronization process, which is basically ensuring that all the TSPs are on the same page here. And this is a small example of the main ISAs which enable this, main instructions. I hadn't heard of any of these until this paper actually, because I'd never heard of anybody using VLIW in the first place.
So VLIW is something that they've introduced, something that.
Oh, it's a thing for sure, yeah. It's been a thing.
Oh,
Yeah, I think a better use case for VLIW would be super small scale CPUs like embedded systems or something, since they're so simple and you can have compiler to do most of the work in that case. They just introduced that over here in a very twisted use case.
I guess another question is like, if all of this like technology existed before, why has nobody tried to fuse it all together?
Yes, so like I said, people have certain extents, like Tesla did it with Dojo, Google did it with TPU, and Habana did it with Gaudi and so on. But no one took it as far as Groq has so like at this moment. There's actually a few more startups doing it, and they're going beyond what you even think. So there's some startups out there saying, let's make hardware for AI so optimized It's not even digital. Let's go back to analog computers. There's startups out there making analog computers specifically for AI, and they look promising. There's a few good ones out there.
So like a computer that is literally just Mr.
Yes.
8x7B.
Yep. So what they're saying is that why does AI need to be digital anyways? It's not like it's not deterministic.
It is deterministic.
No, no, it's not, is it?
Well,
Wait, no.
It's deterministic.
No, not deterministic. What's the word for it? No, not reproducible. He's gonna go mad. Not reproducible. Fuck. I can't remember the name.
What are you thinking?
Probabilistic.
Like binary versus discrete. Oh, discrete. AI is discrete. AI is discrete and it's not, it doesn't have to be binary. AI can be continuous, which is why they were like, why do we need to stick to digital computers when we can just do analog? Since analog is kind of discrete by definition. But there's been no one who's made a wave like Groq yet. They might soon, you never know.
I saw this one video, and it was something like that, where they were, instead of using like conventional binary, it was something like they were using voltages, like inside a chip to use as weights, and then
yes.
be able to calculate, yeah.
Yes, it was really cool, and it's insanely fast, insanely optimal, but it's analog.
Veritasium also had like a video.
Going back to analog computer.
Oh,
yeah.
I was there.
No, like basic, this is that one.
Yeah, no, but
It's like you put it as like, the things that's not like. for
Quantum
example,
is
yeah,
very different from both.
yeah, and then you.
Analog
you use those
is having
They are-
the state as
Yeah.
a baseline.
Video
So
processing.
it enables parallelism for certain use cases, but you can never use it for things like AI, like at the moment. And you can, for sure, never ever use it for general purpose computing, because it's not. One, it doesn't make sense to use it as a single thread, because you're wasting all that potential, and it's gonna be extremely slow. Because of how it is by definition, one, you have functional state at the same time. If you're interested, there's a really cool quantum lab here, by the way. It's a VIP lab, and they hire all undergraduates, and they work with the problem, but they might take. No. There's an ECE class for quantum mechanics, they might be able to take that fast, but it's really cool lab, and they have an actual working quantum computer there. That's it for today. Thank you.
You went for an hour and a half.
You're like, all right, Q&A time.
I swear, I did not feel like an hour and a half at all.